The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content. You can earn continuing education credits through ACI's online CEU program. Visit www.concrete.org to register. ACI conventions provide an opportunity for networking and for keeping up to date with the latest in concrete technology and practices.
Our next speaker is Tengfei. Tengfei is an ACI member and is a doctoral candidate at Oregon State University in Corvallis, Oregon. Tengfei received his Master's of Science and Civil Engineering degree from Oregon State University and received his undergraduate degree from Dailan University of Technology in 2008. His talk is titled, Prediction of Drying Shrinkage for Internally Cured High-Performance Concrete. Please help me, Tengfei, to the stage.
Thank you, Anton. And good morning, everybody. My name is Tengfei. I'm from Oregon State University. Beavers, not ducks. So I'm going to talk about a little bit about the modeling and combination of modeling and the experiment side of the internal curing project. So first, I want to give you overview of the project that's sponsored by Oregon DOT and is going on in Oregon State University. The problem the Oregon DOT has been encountered recently is that when they switch to HPC mix, you can look at the lower corner of the picture, maybe not very clearly, but there's a lot of the transverse cracking, which we think is mostly from drying shrinkage on their newly casted bridge decks. That's probably within 1 year after placement. This is the one particular bridge that's suffering from this problem. So we are trying to investigate the effectiveness of internal cured concrete by partially replace the sand with pre-wetted fine lightweight aggregate and also the addition of a shrinkage reducing mixture to see if we can reduce the long-term drying shrinkage and also for the hope of to shorten the external curing duration, which is now 14 days in the spec. And also a continuation to the project, we are really trying to look at to set up a criteria, shrinkage limits, or if you can put it that way, for the bridge deck mixes, and to develop a simple test method which can be easily used and to evaluate beforehand for the given concrete mixture designs. And to that end, we kind of want to know, we want a pretty good description, mathematical description of the drying shrinkage. What's the development of that thing? So that's where this particular project come in. That's what we did for this project, to try to find a model that will describe the drying shrinkage behavior satisfactorily for our mix with fine lightweight aggregate and SRA concrete, and also with the hope like if you can change different local materials in the near mix. And also we push a little bit further than that. We look at the ACI 209 model, the drying shrinkage model. We kind of came up with a way to do the prediction of long-term shrinkage based on the short-term measurements. So combination of the modeling and also the experimental work. A little bit about the material side. I was going to talk about a little this morning. So we have a couple of different sources of lightweight aggregate, mostly shale, but one source of clay. And most of the work has been done about one shale and one clay. So this curve is the desorption test. The result, the takeaway is that when the relatively drops below 95 and 6%, the moisture is really start to give off. The lightweight start to really give off most of its moisture, give out most of its moisture. And another takeaway is that maybe you can see clearly, yeah, the absorption capacity for clay is almost as much, as twice as much as the absorption capacity of the shale. That's going to affect your the calculation when you want to try to figure out how much lightweight fine aggregate you want to put in your mix. So here's the mixture design. We use a cementitious material content at 633 pounds per cubic yard, and we kept all our mixture design at a worst ratio at 0.37. And we use a ternary blend, which means we plug in we replace 30% of flash, that's the class F slash, and 4% of silica film. And in several of the mix with SRA, there's 2% SRA addition based on this cementitious materials, massive cementitious materials. And also, if you can just look at this list, we have 3 different levels of clay replacement and 4 different levels of shale replacement. One point to point out that the clay at 12% and the shale at 25%, they are identical in terms of internal curing water it can provide. And that's based on the chemical shrinkage test and the advanced equation. And also, we want to try to push it, really to see what's the limit of whether provided lightweight fine aggregate. So we tried 100% shale. That means there's no natural sand in it, just 100% of the shale lightweight fine aggregate. And also we tried a 25% replacement of shale plus SRA to see if there's tension energy going on there. And the targeted 28-day strength is 5,000 psi, 34.5 megapascal. So basically, a lot of work has been done just casting bars. So we did a lot of ASTM-C 157 tests, which is the measurement of free drying shrinkage. We store all the samples in an environmental control chamber with standard condition, and we start drying at different ages, from 1 day, 3 days, 7 days, 10 days, 14 days, and we'll keep tracking the length change. And each measurement is going to be a point for evaluation in the later slides. Okay, some result about long-term drying shrinkage. This is up to 180 days here. You can see the blue line is the control. So what works best is what lightweight fine aggregate plus SRA. That works best, and the one with SRA works pretty efficient too. And the 3D means the 100% replacement of shale works pretty well too. But when we look at the durability side of things, the 100% shale really gives you a problem in the freeze-thaw test. There's a lot of pop-outs, spalling. So this is really just look at the limit of drying shrinkage. And if you look at 2C and 3C, it's almost with the same range with the control, which we think that means if you want to use wetted lightweight fine aggregate to control drying shrinkage, you need a little more than that's calculated by chemical shrinkage. You need more water there to assist hydration to reduce drying shrinkage in the long term. Okay, so we come to the evaluation of the models. There's a lot of information there. Basically, we find out 6 models out there, which has been evaluated by other researchers, used by other researchers, applied in different codes. Let's magnify that a little. So in each of the chart, you can see the calculated shrinkage value. That's from the model on the y-axis to compare with the measured shrinkage. That's all from our lab. This is the designation of the code. Also, if this falls in the diagonal lines, which means a good prediction, and also I give the 2 lines of reference lines plus or minus 40% difference. And up here is the legend. The blue diamond is the control line. This means just pure HPC. and the triangle orange ones are the one with clays, the red dot are the one with shade. Okay, back to this. So 6 models we've been looking at. The HPC 219 model, the CEV90 model, some people I think call it CEV95 or CEV99. That's from a different version, later version of the European code. I think the newest one is called, it's just come out in March, I think, is CEV 2010, which they try to combine the autonomous shrinkage with the giant shrinkage. They're plugging into one equation. But I think the time function in that model is still pretty similar. But that needs some work to update there. And the actual code, which is mainly used for pre-stressed concrete girder, that's really closely related to the HPC 219 model. And the B3 model is the one that with a theoretical basis, which try to explain the physical mechanism behind drying shrinkage. And that model is very alive. I think the newest version is about to come out at the end of this year. Then this model could update too. And also the GL 2000, I put slash here, ALSM model, because they work exactly the same when we look at concrete without SRA. And the ALSM model is developed very specifically for concrete with SRA. Some other takeaways. You can see this, if you really want the dots along this line. So in that sense, the GL 2000 model works pretty good. That's probably because this model is fairly recent, and the data used to develop the model are mostly concrete with cementitious material, supplementary cementitious material in it, like the fly ash silica film. This is like a mostly plus minus 20%, which is accurate enough, I think, for our mix. And if you look at different models, if the curve of the dots changes, that means the time function does not describe very well for the drying shrinkage overlap. Those straight lines, linear lines, means the time functions give us pretty good description, but the arrow majority, mostly from the ultimate value in that model. And then after we look at this, we kind of realize there's some limitations in the modeling, mostly from the data or the concrete mixtures that used to develop those models. So, but nowadays the concrete are so much knowledge is going on there. We have all kinds of different supplementary materials in it. We have different new chemical mixture in it. So sometimes we don't really fully understand what's going on there in all concrete. And there's simply no time, no money to understand them all. It's a lot of them. So what if we can have a mathematical description of the model based on the test? Then we can predict the behavior of the long term. That would be pretty cool. So first we look at, well, what's the characteristics of the drying shrinkage. So basically there are some assumptions are they are monotonically decreasing, and the decreasing rate slows down in time, and also this should converge to a certain point, which makes sense that the shrinkage should stop somewhere down the line. So a good model should have a good accurate description of the time function, as well as a ultimate value this converges to a certain point. And ideally, it should be easy to use. So when we look at all the 6 models we use, there's the ACI 219 really caught our eyes. This is the full version of the equation. You've probably seen the simplified one with this factor set to 1, and this F factor set to different values for different concrete. But if you look at the full function, there are 3 factors, alpha, F, and the ultimate shrinkage value. If you manipulate those 3 parameters using regression, you actually can represent very good about the time function of each of your mix, and you can find give you a reasonable ultimate shrinkage value. So an example, we just randomly select several different mixes from all kinds of work we did. You can see the solid line, the dotted line is the actual measurement, each measurement. And the dashed line are the different models. The solid line are curve fitted using the ACI 209 model. So they really capture the features of this line and hopefully can project to a longer term value, which is reasonably well. And you can usually look at the left corner, the one with GL 2000 model, which works pretty good. You can still see a little bit improvement there. It really captures the time function of the dry shrink curve. So the next step, we did some sensitivity study, because if we want to use it, we need to know how long we can test in the dry shrinkage. So in this chart, this is different meter design we have here, and there's different age. What those number means is we take the measurement up to a certain age, like here if it's 28 day, we just take every data point from 28 day, we plug in the curve fitting program, and what number gives you for an ultimate shrinkage value. And thus we tried a lot of different ages. So what we find out is after a certain age, these values really start to stabilize themselves. So if you compare for the first several mix, that's the control mix, and the one with lightweight fine aggregate in it, they are really, after 50 days, around 50 days, if you compare to the 180 days, you use the data up to 180 days to calculate to fit for the ultimate shrinkage values. Most of the difference within 5%, which is reasonably well. And this is kind of based on the assumption that the longer term we use is going to give you a better prediction. And if you look at the SRAs, that's because SRA is really slowed down the development of the dry shrinkage development. So you need a little longer time. In our test, in our case, we're thinking about 90 days. It's good enough to predict long-term shrinkage. Another point is that this is still kind of under work. We need to know, we kind of want to know, how can we stop the test during the test? Like, you cannot just do 6 months or even more longer test to know that, okay, 50 days, good enough. So basically like what, 134 months. But that part is still under work. We are looking at the shrinkage rate, which is the first derivative of the curve. We are going to look at the acceleration of the rate of the shrinkage. That's the second derivative of the curve. We even look at the shrinkage completion rate. We look at several different other things. We have some idea. There's some trend, but nothing at this point is conclusive. We're still trying to understand the math behind this mathematical form. Then really stop the test during the test, give it the criteria. Believe it now, we're starting to look at Taylor's theory, if you remember what that is. Okay, so at this point, the proposed procedure. So you perform the ASTMC 157 test, you keep tracking the rate shrinkage. After 28 days, you just start perform the curve fitting. It means you plug in the data ahead into the full equation and determine all the parameters and find the ultimate shrinkage value. And you keep tracking those until you find it satisfied, it's stable. For our mix right now, it's really 50 days for the HPC, and the HPC with fine library aggregate in it. 90 days, that's a little longer for SRA in it. Several conclusions from the dry shrinkage test, the first dry shrinkage test. The SRA works pretty efficiently, and the synergy with SRA and fine library aggregate works the best. We have some hypotheses and have some work. We want to continue with the direction to really understand it, and also to achieve less dry shrinkage in the long term, just by using the chemical shrinkage the dense equation is not enough. You kind of need more finite aggregate to help with the branch shrinkage part. And also, there's one conclusion is possible to predict long-term shrinkage using the ACI model. It's based on short-term measurement, but we are kind of just over 355 days, the 1 year mark now. We want to keep tracking it to verify it, maybe very long term. I'm thinking about 3, 5, maybe 10 years of data to really see this direction converged at some point. Okay, future work. So as I said, collect more data to verify this proposed procedure. Another side of the work is, alongside with the model, is to understand the science behind the physical mechanisms of drag shrinkage. That will help with the modeling. And also trying to understand the mathematical features behind this behind this equation. See if there's anything we can do to stop the test just during the test. Also, we ultimately want to use this model in the project we talked about at the beginning of the presentation, in the joint shrinkage criterion. We want to plug into some program along with the ring test, all the other mechanical property tests.